This
And
conference will now be recorded.
oh, just been told it's been recorded. Great. Yeah, thanks for the introduction, Andy, and also for the opportunity to talk to everyone who's joined the meeting tonight. Um, Basically, going to start off by kind of giving a bit of a brief history of data collection, not right back to the very start, but sort of my experiences. I'm going to cover some of the more recent developments on the measurement fleet and in the area, looking at our kind of move towards a more predictive maintenance regime and preventative rather than kind of a reactive regime to sort of faults that are being output by the various systems. I'm going to touch on our intelligent infrastructure program, looking at how we're exploiting all of the asset data that we collect. And the final part is some of the R&D activities that are going on in this area that I'm just going to touch upon, and just to try to give a flavour as the sort of breadth of the work that's going on and the sort of depth of development that's happening. So I just thought I'd start the presentation with a sort of a collection of some of the stranger vehicles that sort of come across during my time in the email exchange with Andy and Andrew over the sort of setting up of this meeting. Andy actually mentioned that he'd been on a vehicle very similar to the Porcupine vehicle on the left, basically a gauging vehicle that had some spikes sticking out of it to actually physically measure the clearances to structures as the train travelled down the track. I've had experience of the photo in the middle of our optical car, which I think was built in the 1980s. Probably seemed to be quite state of the art at the time. Effectively, built from a freight wagon, which allegedly had a twisted chassis, so or an underframe. So no doubt we picked that up quite cheaply. Fitted some lights onto it, fitted some cameras onto it, and using a triangulation measurement method, we travelled around the country measuring the structure gauge through that approach. First-hand experience of being inside that vehicle with 40 or so of the halogen lights having been on for a number of hours, and the temperature was sauna doesn't do it justice. So some interesting stories over the years from working in this area. And then the final picture on the right is a sort of current, I guess, state of the art, which I know as some of the people from the Wales route will have some first-hand experience of the Reeler system, which is effectively a modular gauging system, track centerline surveying system, video surveying system. It's a sort of system of the future, really, covering capturing lots of different data that can be used for lots of different purposes. I've just put a couple of links on there that I would ordinarily have sort of shown during my presentation, back to some of the measurement train footage from the Pathé British Pathé website from the 1950s. So something that you can have a look at in your leisure. I didn't want to breach any copyright with the meeting being recorded. So my experience, as Andy said, started in the rail industry in 2000, September 2000, and yeah, shortly after that, something unfortunate happened that was, well, obviously changed the way that we maintain and measure our infrastructure. It's the accident at Hatfield, 17th of October 2000. Fortunately, 4 people lost their life. A rail break caused a high-speed train to derail, I think, more than 100 miles an hour. Rolling contact fatigue was identified as the cause of the rail break. So effectively, surface cracking in the rail being left untreated and propagating down into the head of the rail, and as you can see by the picture, caused the rail to shatter into loads of pieces. And as I mentioned, 4 people lost their life in that accident. So that was very early on in my career, 6 weeks into my career. There was massive disruption to passengers, as the graph there shows, sort of ppm down to sort of 75, 76%, huge disruptions, huge delays. And the I guess what I'm going to talk about in the next few slides is kind of really as a result of this. There was huge investment in infrastructure measurement, both technology, trains, and I'm going to describe some of that. So the first thing really that came out of that was a real look at our rail testing and rail management regime, introduction of the ultrasonic test units, which, as I'm sure most of you are aware, run around our network using ultrasonic probes to test our rails, to identify internal defects within the rail. And some of the pictures on this slide really just show left-hand side the probes on the vehicle, and then on the right-hand side at the bottom the kind of makeup of the probes that are fitted to the train. So there's ultrasonic probes fitted in within roller search units, so the tires are they compress as they press against the rail, roll along the surface of the rail, and fire ultrasonic waves into the rail, different angles, looking for different types of defects. And this has been hugely successful in terms of improving our rail management regime. Just as a bit of a kind of overview of some of the types of defects that these systems detect, kind of broadly broken down into 5 different categories. So head defects, which is sort of the images on the top, rail foot defects, which are proving to be difficult to find, and as you'll see a bit later, sort of making up a larger and larger proportion of the number of rail breaks that we have per year now. Also weld defects, so faulty welds, again, the numbers here have reduced drastically, and there's also rail hole breaks from star cracks at bolted joints. So as you can see from these pictures, some pretty catastrophic sort of results if this is left unchecked. So as I mentioned, introduction of the ultrasonic test units. So 1999, 2000, year of Hatfield, 900 or more than 900 rail breaks per year, and now, although the graph doesn't go right up to today, it's consistently about 100 breaks per year, which is a massive improvement. I guess the other thing to consider about that is the sort of the backdrop of that is that over that time period, traffic has probably gone up by around 50%, and access to the railway to actually perform maintenance has reduced drastically, so much less access to actually get in and intervene. So yeah, obviously the UTUs were not entirely responsible for all of that improvement, but they were a very large part of that. So obviously some good coming of the catastrophic sort of events at Hatfield. I mean, I mentioned earlier about different types of defects. So just a bit of an analysis here around the types of defects that were sort of prevalent in 2010, 2011, which is the pie chart at the top. So sort of 30% welds defects, 16% rail ends, 40% rail foot. 5 or 6 years later, weld defects halved, rail end defects halved as well in terms of percentages, and rail foot defects making up a much greater percentage of the total number of breaks. These slides, courtesy of for Brian Whitney, as a sort of resident NDT expert, but just sort of showing the size of the challenge that we have now to try to reduce rail breaks even further. And there are initiatives in place looking at trying to get numbers down to sort of 50 breaks per year by 2030, and maybe even down to 30 breaks per year by 2050. But with a percentage of breaks caused by foot failures so high, that's proving to be difficult to crack just using technology, measurement technology on its own. In addition, so I joined Network Rail in 2006, and there was a huge amount of investment going on in the measurement train fleet at that point. So as well as the ultrasonic test trains measuring the rails, there was also rail profile equipment fitted so that we can measure side wear, head wear. There's ground penetrating radar fitted. That was one of the first projects I worked on at Network Rail, bringing that technology in. I'm just going to say a little bit more about that. So yeah, fit the first batch of GPR equipment in 2006, trying to understand track bed condition, trying to understand whether we could identify this sort of early onset of wet beds, whether we could do more to sort of determine where renewals were required versus where maintenance would work. And yeah, these pictures on the slide here just show the GPR antenna fitted onto the measurement trains. It's the black box that you can see there. That's hopefully that's popping up on the screen, and the white box on the image on the right that houses the antenna. We trialed a number of different antenna, looking for see whether we could spot different depths of features, and the radargram on this slide here just shows that the layers in the track bed that it's possible to see between old ballast on the left hand side of that picture and new ballast starting here, and you can see a really clear interface between the clean ballast above and the formation. So this was quite a useful introduction, and in fact so useful that in 2009 we actually upgraded the equipment. So we fitted some effectively higher resolution antenna, 2 gigahertz antennas, so that we could really get a detailed look at the ballast condition itself, and look at kind of the fouling levels within the ballast. So where was suitable for particular types of treatment, whether it was suitable for tamping, whether it's suitable for or whether it required ballast cleaning, or maybe even whole track bed renewal and drainage as well. So these color coded charts here showing blue is particularly highly fouled pieces of dirty ballast, green is clean ballast. So this was again providing the maintenance engineers and also the renewals teams with information about their track bed and what treatments might work best for them. So Andy mentioned new measurement train. I worked on the geometry system that was fitted to that vehicle whilst I was at AEA and tested it. Came into service in 2003. And yeah, it's still, almost 20 years on, still the flagship of the measurement fleet. Probably could do with a new name, not so new anymore. But yeah, it's running around our mainline track. It's recording track geometry. It's recording track intervals, separation between tracks. It's got plain line pattern recognition, video inspection equipment fitted to it, high definition cameras, and there's also overhead line equipment fitted, so non-contact overhead line measuring wire heights and staggers, and also wire wear. So it's a bit of a Swiss Army knife of measurement trains. I think the only thing it doesn't do is the ultrasonic testing, and that's just due to the fact that the equipment doesn't operate at the speed that this train runs at. I've mentioned gauging a few times, so it's kind of a key thing that the fleet does. So making sure that vehicles fit through the sort of structures that are around our network, and also making sure that they can pass each other safely. So tracks are far enough apart from each other. Again, this is another project, another area that I've worked in quite extensively over the years. So this saw the black optical car on the first slide as I started. This again was a sort of a fairly project that I started working on sort of soon after joining Network Rail, basically to move away from the white light measurement system, which had as well as the high temperature that was the lights caused within the actual vehicle, There were some reliability issues. There were some data accuracy issues. So we moved. This was our first step into using lasers for structure gauging. So we fitted the laser flex system. Basically, sort of very quickly became known as the dustbin that was fitted to the vehicle. So it had, again, similar principle to the white light system that I mentioned. So it's shining laser lights out perpendicular to the track, and cameras looking back towards those laser lights to establish how far away from the system the structures were. And just a picture there showing the red laser lights coming out of the system when we were doing some testing. It's a successful project, so you can see the data quality improvements that we got from doing this project. So left-hand side is our sort of new data with the laser system measured at a station. So the old system struggled in areas where there were high levels of ambient light, and the image on the right just backs that up. So this was going through a station. There's just a huge amount of noise on the data due to the station lights, due to the built-up area around, meaning that a lot of the data that was collected had to be thrown away. Whereas with the new system, it's pretty clean, and you could not have to throw away data so often. Finally, I think in this section is Mentor. So Mentor is the oldest measurement train in our fleet. I think it's 60-something years old now, and it's overhead line measurement. It's a contact system, so it has an instrumented pantograph fitted to it that measures the force between the wire and the pantograph. It also measures the dynamic height and stagger of the wire, and also the acceleration. So it's giving you all the information you need to understand what the pantographs on passenger trains are experiencing as they're traveling around our network. It's limited to 100 miles an hour, so a bit more on why that's an issue for us later on. But we've recently upgraded the equipment onto it on the train. There's a sort of another story about infrastructure measurement. The picture here on the left is the previous instrumented pantograph that was fitted to Mentor. It was unfortunately involved in a dewirement in August 2012. So we just had a new system fitted. We were just commissioning it, just getting it into a working order, and it came along and went through a section of track that had recently been maintained. The registration arm had been left in the wrong position. Mentor came through, hit the registration arm, massive flashover, bent the pantograph arm out of shape into the shape you see there, and fried all the measurement equipment. So that was a particular sort of own goal for us. But yeah, pleased to say that the picture on the right is now Mentor reinstated. That was taken at Old Dalby. Testing that was carried out at the back end of 2019 to commission the new system, and it's now out and about collecting force and acceleration, heights and stagger data. So yeah, managed to rescue that, thankfully. So I'm going to cover some of the more recent developments that have been in this area. I say recent-ish. Some of them not so recent, not that recent, but still quite made quite a fundamental change to our measurement fleet and the way it operates. So the main change since probably 2010 has been introduction of plain line pattern recognition, which I'm sure most of you have heard about and probably know a bit about. Effectively, it's a video inspection system. So it's targeted at reducing the amount of visual inspection that's required of the track. Yeah, obviously huge safety benefits, and also gives the ability to look at sort of trends and look at how things are changing over time. So rather than it being a kind of a one-off inspection, you can look at like faults over time and the numbers and how they're changing. It's based on a camera line scan camera system. So as the picture shows here, there's 7 cameras fitted underneath the train, 3 looking at each rail and 1 looking at the forefoot. There's also laser scanners to build up 3D pictures and 3D representations of key areas, so particularly around the fasteners. There's also ballast shoulder lasers that will help that are there to detect ballast shoulder levels and also the level of the ballast within the crib, so that they can be reported if there's insufficient and potentially a buckling risk. And there's also, although from a separate system, track geometry information is a key feed into the PLPR collection process. So as I say, this is a measurement train borne system. There are, and in addition to NMT, there are 4 other vehicles, and they operate on a 4-weekly cycle around the plain line sections of the network. The process is that basically the data is collected on the trains. The on-train technicians ensure that the data is collected and recorded onto a removable hard drives. Those removable hard drives are then couriered from the train back to our office, mainly due to the fact that the volumes of data that are collected are huge, sort of multiple terabytes of data per shift, and it's just not possible to wirelessly or to any other way get that data back to our office for inspection. When the hard disks land in the office, they're plugged into our off-train processing system, which effectively brings all the different data sets together. I mentioned on the previous slide the different images, the different camera views, laser profile, location information, track geometry, brings all those data sets together, identifies out of all of the data that's been recorded which track sections are supposed to be inspected using PLPR, and cuts that into the relevant journeys, and then applies machine vision techniques to the images to identify features of interest. So some of the items that are being looked for, so things like missing clips, as I mentioned before, high ballast, low ballast, and then there's also some things that are looked for that are triggered by the track geometry. So if there are dip angles or if there are particular types of faults. There's a time scale on the data, so within 48 hours of collection, the data has to be processed and ready for inspection. So once the machine vision component is completed, it presents our examination inspectors with a number of candidates. So potential, I guess, think of those as potential faults, and then the examination inspectors step through the faults or the candidates, looking at them in a bit more detail. Is it a genuine fault? If so, report it in the appropriate way, depending on what kind of fault it is. If it's not a genuine fault, then mark it as a false positive. And then within 72 hours of collection, the reports have to be issued out by the examination inspectors to the front line. And this table here just summarises the defects or the faults that the system is looking for, and how the system determines whether that to spit that out as a candidate. So as you can see, some of the faults, the top 5 are triggered from looking at the actual PLPR data, so either the laser scan information or the camera footage, and then the bottom 6 are triggered from the geometry. So if there's a geometry fault, there'll be a check on whether whether there's misaligned base plates or whether there's visible defects in the head or an IRJ there. There are some changes being looked at the moment in terms of can we get more information, better information from PLPR, and I'll touch on that a little bit later on. Another one that's a fairly recent development is eddy current testing. So as I mentioned at the start, the Hatfield accident was caused by rolling contact fatigue, effectively rail surface cracking that was left and resulted in the cracks heading into the head of the rail. So we've fairly recently been working on eddy current testing, so to complement the ultrasonic testing really. So ultrasonics is capable of measuring from around 5 millimeters from the surface of the rail. Eddy current's really good at measuring the first 5 millimeters. So if you've got eddy current and ultrasonics, you're getting a very comprehensive and kind of complementary view of the health of the rail. So this next slide, which I've stolen from Brian, is just a kind of a very simple description as to how the equipment works. So there's a coil which has a current pass through it, induces a eddy current in the surface of the metal, and which is the second part. And then if there's any flaw or crack or within the rail surface, that will affect the eddy current, and the effect can be measured. So if I just get back to the previous slide, there's 10 probes across the head of the rail. So each one of those probes is effectively doing this and identifying within its sort of sphere of measurement whether there's anything that's affecting the eddy current. I think the big step forward with eddy current, train-borne eddy current testing compared to the previous manual process is that the output is the depth. So it's the depth of the cracking rather than the manual process was measuring the longest crack within a given section of rail. So it's really the depth that you're interested in to give you the risk of a sort of an internal defect developing. So on to some of the work we're doing to look at kind of a more predictive and preventative maintenance regime. So I think it's I think this graph here really sort of shows the situation that we've probably been in for probably a number of years, where we send measurement trains out around the network. They measure the various different parameters that I've talked about already, and effectively issue faults out from the train. The severity of the fault determines how quickly you need to react and what action you need to take. I guess from a track geometry point of view, in the severest situation, if you get a block the line fault, you've got to block the line to trains. I mean that the number of block the line faults is fairly low, but that's still a very reactive sort of way of working. I think over the last sort of 5 to 10 years, there's been introduction of alert limit faults, which is trying to get sort of away. So from on this sort of P to F curve, it's trying to get further away from the point F, which is where a failure occurs. So you get more warning, you get more time to plan an intervention, potentially plan the right intervention, and that's all underpinned by regular data, reliable data, and also having the right sort of analytical tools to be able to take that data and kind of work out those sort of intervention points. I think sort of my personal observation is that our measurement train fleet has been really very good, as the sort of graph on rail floors showed, rail brakes, sorry. It's been really good at reducing our sort of critical safety risks, so rail brakes particularly. Maybe where there's not been so much focus from the train fleet certainly is kind of the performance risks, so the impact on the passengers. I guess this slide here is quite an old slide, but it's still very relevant. It still describes the current process that we go through. We collect data, we send defects through to fault management, we take data off the train. quite funny to have a floppy disk on there, but it's pretty much the same process with the portable hard drives. We do data processing, reports, load data into systems, and yeah, there's probably still quite a lot of paper sort of being used in maintenance in terms of looking at the outputs and even like overlaying different outputs. So when I move on to intelligent infrastructure, there's more of a description on kind of how we're trying to get away from that, how we're trying to do things more intelligently. I think the main point of this slide though really is that it's still quite reactive in terms of the process that it drives. And reactive maintenance is a problem for us really, because probably it's quite inefficient. Our access is reduced hugely, so sort of being able to work in a reactive way is difficult. It's from a performance point of view, you can see on the top graph on the top left, that's our sort of ppm over the last 10 years or so. So the red is the actual ppm. You can see that there's just been a gradual decline. The black is the target, so we've kind of tried to re-baseline targets and then failed to hit them, re-baseline again, failed to hit them, re-baseline, failed to hit them. So it's a bit of a pattern there. It's probably worth saying, obviously, the traffic volumes have increased over that period. What's very interesting to look at though is in terms of number of service affecting failures. So the number of service affecting failures has reduced year on year over the last sort of 10 or so years, maybe even longer. But the delay per incident is increased. So effectively, each failure that does occur is causing more and more, is causing a bigger problem, a bigger delay to passengers. So when we come to think about all the work that's gone on with the what used to be the sort of intelligent infrastructure program, so embedded monitoring equipment. So summary slide here showing the amount of monitoring equipment that we've deployed trackside to reduce service affecting failures, power supplies, track circuits, point heating. All of those things have contributed to that reduction in service affecting failure numbers, but still the delay minutes and the ppm figures have continued to increase, and sorry, the ppm figures we've continued to struggle to hit the ppm figures. I mean, just a little bit more about the embedded monitoring and the approach to embedded monitoring. So there's a lot of data available from the various sensors and data loggers that are fit trackside. Analysis has taken place on that data to establish the sort of patterns and profiles. I guess much the same as PLPR really. So it's looking for patterns of particular types of failures. So this example here is point condition monitoring. It shows the different waveforms from the point motors and the types of faults that can be identified from those waveforms and a condition assigned. So you can start to become more preventative and act on the data rather than waiting for something to fail and then going out and having to act on it. And there's more embedded monitoring work going on. Buzz bars, level crossings, embankment monitoring are all things that are being worked on at the moment. And this is just an example of embankment monitoring with inclinometers, also cameras, so that you can start to I guess verify what it is that the system's telling you, rather than looking at a particular sensor on a particular piece of embankment, and going out and finding that actually somebody's dislodged it and animals burrowed underneath it. If you've got the footage, you can start to go out to site in a more sort of, I guess, in a more educated sort of way, knowing like roughly what you might find and knowing roughly what you might need to do when you get there. The other thing that's, I think, going to help a lot with becoming more predictive and preventing service affecting failures is data from passenger trains. So pick two images here. Image on the right hand side is some of the Hitachi Intercity Express vehicles with track geometry equipment fitted to them, running Wales and Western, and that particular one, and also East Coast. That's something that's been a long time in coming. It's something that will definitely sort of help with the kind of more monitoring approach to linear assets that's been adopted with the embedded monitoring program. So more regular data, looking at trends, looking at changes over time, and predicting when it is you need to go and intervene. The Pendolino on the left hand side, I put that there. So as Andy mentioned, one of the pieces of work I've been involved with is how we collect data best in the future. So this is an example where we need to use passenger trains to measure our overhead line. These trains travel at line speed. Our 60-year-old Mentor vehicle only travels at 100 miles an hour. So we need to we're in the process of selectively deploying overhead line equipment onto passenger trains. One on West Coast Main Line, Great Western Main Line, East Coast Main Line, and also talking about East Midlands. So that's going to be more regular data, again, predictive. Opens the door to sort of predictive capabilities that we can develop, which brings me neatly on to the Intelligent Infrastructure Program and our sort of plans for exploiting all of the data that we're collecting. And apologies for the change in the transition there between the slides. It's just I just ran out of time to go through and change the formatting of slides and change the transition points. But I thought the other way of looking at it was at least it shows that these aren't my slides, so a bit of a reminder to credit the Intelligent Infrastructure for these slides. This slide really just shows kind of at quite a high level a lot of the work that's going on, sort of fundamental work within Intelligent Infrastructure, to make sure that all of the data that we collect, whether it's from aerial survey, train-borne, remote condition monitoring trackside, all of it's available in a common analytics platform, so that all the data can be brought together, so we can understand what's track geometry against points condition monitoring. Is the geometry bad? Is it causing points motors to start to fail prematurely? All sorts of things along those lines. And the next slide is a similarly kind of high-level view on an end-to-end process for collecting data, validating it, mapping it, comparing run on run, so that we can look for changes, bringing it together with the sorts of relevant data that are useful to give an overall picture as to how the asset's performing and what the treatment, when the treatment might be required and what treatment might be the best treatment. Visualization in box 8 there on the right hand side, and then bringing that into our into Ellipse effectively. So work orders, defects. If we're going to start to make greater use, particularly of passenger trains, all of this sort of process needs to be automated. Otherwise, you just quickly run out of people to work with all this data. So I'm sure some of you, or maybe hopefully more than some of you, will have seen our the work that's going on with our enhanced decision support tools. Again, this is about the data. It's about bringing in multiple sets of data, overlaying them as shown in this example. So multiple track geometry recording runs on this trace here, brought in, aligned, and then as I go to the next slide, looking at how things are changing over time. So these are all the data points. This is the rate of deterioration, and the dotted line showing the predicted deterioration, predicted degradation. So when's it going to hit the alert limit? Sorry, when's it going to hit the intervention limit? And look so that you get as much early warning as you can in order to plan the right maintenance intervention. And yeah, just to summarize that in a table there. So the columns on the right is telling you when it is that the fault is predicted to get alert limit and when it's going to hit immediate action limit. So again, useful information, helps us to become more predictive around our work and less reactive. So that's just for track geometry, but the plans are to build similar capability within looking at rolling contact fatigue, so or eddy current surface cracks, rail flaws from the ultrasonic systems, rail wear from rail profile, rail depth, ballast information from GPR, all of the data streams that I've mentioned already in the presentation are kind of going down that route with decision support tools, predicted rates of deterioration, and looking to use that to become less reactive. I think one other thing just worth quickly touching on is, so it's about criticality of the system, the railway system. So trying to understand what the impact on the timetable is. So it's not just this piece of railway is predicted to fail soonest, so let's go out and fix it. If that particular piece of railway has one train a day versus another piece of track that has 100 trains a day, you need to be going to the right place. So this sort of time lapse images on the screen here just show kind of how the like ripple effect of if there's a failure at a particular place, how long it is before it sort of ripples to other. So a failure at Cheltenham in the morning is being felt across the country within less than a day. So trying to understand the railway as a system and trying to understand impact on timetable as well as predicted time to failure is also something that's being looked at through intelligent infrastructure. And I think the final thing before moving on to the R&D part is looking at combining different data sets to determine the right treatment. I've touched on it previously. Here's an example just of from a rail perspective, looking at on the left-hand side here, some RCF type marks and surface damage, the output from the eddy current system in the middle showing depth of crack and severity of RCF, rail profile information, rail depth information. So all of that, using that information to build a picture to try to advise what type of treatment to do. So if the cracks are greater than 5 mil, probably need to re-rail it, because a bit less than that, maybe get away with milling it to remove the cracks. Then it moves into milling or grinding, or grinding if the cracks are really quite light, and just kind of try to keep them at bay. Similarly, from a track bed and track perspective, I know that probably can't see the detail of the chart on the right hand side, but effectively it's bringing in information about components, about age, about track quality, layout, looking at deterioration rates of track quality, looking at the core samples, sort of showing like material types, ground penetrating radar, showing the layers within the ballast and the ballast fouling a bit further below. And it's using that information to determine what the right treatment is for a particular section of track, and advising that. So is it tamp? Is it stone blow, ballast clean, total drainage renewal? and the sort of power of the data there, it allows you to kind of make those decisions by being able to bring all that data together. So I'm just going to finish off by quickly going through some of the R&D priorities. So there's a in CP6 there's a huge R&D portfolio within Network Rail, looking across. It's been sort of restructured slightly, looking across different sectors, so different sort of priority areas. So ease of use for passengers, emissions, optimized train operations. Probably the main two that I get involved with are reliable and easy to maintain, and data enabled. So probably data enabled being the most the thing I get most involved with. So I'm just going to touch on a few of the projects that that are kind of going on that are sort of within the area of infrastructure measurement. So within the track maintenance and plant, there's a whole load of initiatives to do with components, to do with future S&C, future track, cast crossings. But there's also a lot to do with monitoring. So things like well, there's robotic inspection and maintenance vehicles. So a piece of work looking at whether we can build a rail test vehicle and also a vehicle that can fix sort of do a weld repair of squats. There's enhanced rail floor detection that I'll pick up on in a bit. S&C measurement train. There's a whole load of systems covering a wide range of areas here. I think one of them that's fundamental to all of the stuff I've just been talking about is locational accuracy. So one of the pieces of work we've been working on for the last 2 or 3 years is this piece of kit here that's fitted underneath our new measurement train. So it's effectively a camera-based system that's going along the track. It's taking images as shown in the the image on the bottom here, and using the images captured of the track to look at effectively a barcode, creating a barcode of the track, so that when you're recording one particular piece, another piece, you can align the different sections of track and know that you're in the right place because of the unique features that the cameras have detected. And that's given us, from the testing that we've carried out so far, a locational accuracy of 6 centimeters as a standard deviation. So that's probably a couple of orders of magnitude better than we're currently sitting with the location systems we're working on. We're using at the moment. So that could be potentially a game changer in terms of bringing together the different data sets more easily, rather than having to do a whole load of processing on that. There's S&C inspection, so both from a sort of a robotic point of view, piece of work, looking at measuring the profile, looking at measuring the clearances, contact angles and things like that, using the Felix robotics solution. And there's also a piece of work that's just started where we're looking at a kind of a train-borne version of S&C inspection. So building on track geometry, building on the work done with the MPV to measure track geometry in stations, looking at vision, looking at the profiling, sort of similar to the way that the Felix system is being used. I mentioned enhanced rail floor. So although the UTUs have been incredibly successful and useful, there's still big opportunities to improve things. So combining the outputs with images of the rail is something that's really useful. Helps to try to reduce false positives. We want to try to move towards a place where we can reduce the amount of manual verification required, because we can do some more intelligent kind of analysis and reduce false positives before data is issued. Yeah, so I've mentioned before, access is reduced. So that's another driver for reducing verification. We want to try to increase the speed at which we can record. So running around at 30 miles an hour, whilst key critical activity from a safety point of view is not very conducive to running freight trains at 60 or 75. And also it gets in the way of it. So running 30 miles an hour at night gets in the way of possessions. So those two things conflict with each other. And the other part is detecting types of faults that currently aren't detected very well. So vertical splits in pre-76 rail, and also foot defects is something I mentioned. So a greater proportion of rail floors of rail breaks are from foot defects. So that's something that we need to be looking at in this R&D project. Driver reported rough rides is another piece of work where we're trying to reduce the impact of drivers reporting rough rides. So trying to understand where rough rides are likely to be reported due to vehicle response monitoring, looking at whether we can do some sort of simulation type work to understand what a safe speed might be if a rough ride is reported. So we've been doing some work with ProRail in Netherlands about that. Some system that they use where they can say actually 80 kilometers an hour is a safe speed for this type of vehicle, rather than a standard sort of 5 or 10 mile an hour caution. General assumption is there's something wrong with the track when there's a rough ride. So again, if we've got monitoring equipment fitted to trains, we can identify sometimes it might be a combination: poorly set up vehicle, poor piece of track. Just backed up by some numbers from some 2018 data that we looked at, where there was 68% was no fault found when rough rides were reported. So part of that might have been locational accuracy, part of that might have been because it might have been a combination of vehicle and track and sort of difficult to find. So yeah, so the work we've done so far shows that geometry on its own is not a good indicator of rough rides, which has led to so it just shows there that sort of good section of track, but rough ride reported there. So it's just sort of backing up that work that we're currently carrying out, where we're introducing a number of different monitoring systems onto a fleet, and we're going to be looking at the number of potential rough rides that those systems predict there will be, and then correlating it with the number that actually do occur, and looking at whether we can improve the process and reduce the impact of service affecting failures caused by rough rides. So also within the area, also within R&D, probably the other key work stream I'm involved with is reliable and sustainable power. So primarily overhead line and conductor rail. So this is a piece of work that Wales and Western are leading on, which I was involved in the early stages of, but it's got huge potential, which effectively is using the pantograph camera to look and identify the wire height, the wire stagger, and estimate the force between the wire and the pantograph. So potentially all new vehicles that come equipped with pantograph cameras become monitoring vehicles. So you get huge volume of data, huge ability to monitor change over time, and also ability to spot things that have changed quickly. So you can potentially prevent incidents, and as everyone knows, this sort of overhead line incident has caused huge delays and huge impact and huge cost. There's some work we've been doing with pantograph camera footage as well. So from Mentor, getting the video off the train quickly into a web portal and marking the web portal with exceedances. So these exclamation marks you can see, hopefully here, show the locations of exceedances from the measurement system, from the instrumented pantograph, and the corresponding video footage. So you can see this location, the wire is on the horn of, well onto the horn of the pantograph, which obviously have big derailment risk. So again, kind of bringing together different sources of information, verifying measurement data with video data is a key sort of area of focus. And we've been, other things we've been doing with conductor rail. So we're currently working on the replacement system for measuring conductor rail profile and wear, but also position relative to running rails. Looking at also the impact between the conductor rail and the shoe, so some sort of force measurement, and also we've carried out some thermal imaging trials to look for hotspots. So this particular cable coming in here, there's a hotspot been detected. Again, we've used portable cameras fitted on the front of trains for doing passenger carrying trains for doing this this work. And I think that's it. So thank you very much for listening, and happy to take the questions.
I'm muted.
Is Andy there?
He fell asleep.
I doubt it.
That's suggested. Yeah,
I hear some rumblings.
obviously got his microphone muted.
Right, sorry about that. I couldn't unmute myself for some reason. Can you hear me now? Yeah?
Yes, we can hear you now, Andy.
Right.
Thank you. Take over.
Okay, yeah, so sorry about that. Right, so we have got a couple of questions come in. So Andrew Wilson actually poses quite an interesting one as about the whole sort of how the structure of this is working. And he's asking the question, with predictive work from decision support tools, who has the ultimate responsibility for safety of the line? And how are we going to actually support people with that kind of information? So things like lowering the speed and that, how do we actually support people doing that?
Yeah, I think there's been some discussions on that kind of thing, particularly with regard to the decision support tools, and I think it's been quite well, to me anyway, it's been quite clearly made quite clear to me that they are decision support tools, so they're there to help the maintenance guys make the decision rather than tell them what to do. So I think
My phone sorted out.
Well, I'm celebrating. I had a gin and tonic and I don't mind.
You are a win. You're very lightweight, aren't you?
Right, carry on, sorry. Okay.
Yeah. Okay. So it's very much seen as a decision support tool rather than a sort of making a decision for somebody. So it's kind of providing information, sort of extra information, say, to help with the decision making process.
Yeah, to support that, the emphasis is very much on this is it's about processing the huge quantities of data we generate now to create information that supports people like section managers and indeed track maintenance engineers at the moment, but it'll be other functional engineers in due course as well, to actually help do their work. And it really continues the principle that we've had for a long time with track recording, which is one, if the system, you have sufficient confidence in the system that if it doesn't tell you there's something you should be looking at, it is good, which is a really important thing. So don't forget that sort of the opposite side of it. But it is, it's about presenting people with some information backed up with sort of statistics that say when these things start to come together, you are very likely to have this kind of problem and you might want to look into this a bit further. Okay, right, the next question is from Andy Batters. Says, hello, Kevin. I was part of the network rail team that procured and managed the introduction of BCS4. Yeah, I know this was sometime 10 plus years ago. We tried to specify some high-speed camera systems to take ballast bed photos during ballast cleaning when the top ballast was removed and the bottom ballast and formation were exposed. But at the time, there seemed to be little appetite to progress this one. One of the reasons cited was no central data store. So it was interesting to see your model of data and central storage. Have you or Network Rail any new thoughts on ballast bed photos with today's more advanced technology and your centralized data storage?
I mean, I think
this could be a very quick answer, but
I think from the data storage point of view, there's the sort of media and survey platform that's being built that's supposed to be housing all that kind of data. I think there's definite appetite to be bringing in all data that potentially could be useful. I think with this one, the difficulty would be in terms of, I guess, the focus of the Intelligent Infrastructure Programme is around improving maintenance, which probably is slightly too narrow for this, which might be more of a renewal tool. But then it potentially would be quite sort of short-sighted to ignore that source of information, because it obviously can tell you, it can inform probably about condition of the subballast, which would then give you an indication as to how likely how long something's likely to last before it starts to deteriorate. If that's in poor condition, and then you just go dump a load of clean ballast on top of it, then it's not going to last as long as whether it's in good condition and you do the same. So I think maybe I'm not really sure where to take that, but I think it's certainly a good suggestion.
yeah, again, to support on that one. I mean, one of the things that we're getting out of things like the decision support tool is the power of combining lots of data streams. So rather than just looking in track geometry in isolation and rail defects in isolation, we're now starting to see the power of combining the two and looking at the implications of track geometry faults on rail degradation and things like that. So I think that will also, I think the other thing which has really changed in terms of making this available is we're now moving towards, and you might want to say a bit more on this, Kevin, we're now moving away from here's a load of data, we'll send it to you, to here's a web-based system where you get sent a link which says the data's just been updated, you can go and have a look at it now. So rather than having to transfer a load of information out, you now go in and look at the information in some central repository. Because for a long time, we reached the limits of what you could sensibly send. It was just too big. And as soon as you get video involved, the data files become vast. Yeah. So that's been a big change as well. I don't really want to say anything further on that, Kevin.
Yeah, I mean, not necessarily specifically to the ballast bed photos, but the example I showed of the overhead line video from our Mentor vehicle and the exceedances marked up on there, that kind of just, so the current, this is a sort of a trial that we've been doing over the last 6 months. The current process for Mentor video and instrumented pan data is to send the instrumented pan exceedances out, and then it takes anywhere up to 6 weeks to get the video available for people to look at, which just seems ridiculous in this day and age. Whereas the trial we've been doing, the video and the exceedances are synchronized together and available within an hour. So yeah, I guess you could apply that same principle, and they're available, as you said, Andy, on a web portal. So no data needs to go anywhere other than, you know, between your computer and the web portal where the data is hosted. So
yeah, plain line pattern recognition works the same way. Whilst we take a huge amount of video of the track, if you're on the receiving end of report, you only receive
Yeah.
pictures from the immediate vicinity of the fault, rather than get sent a huge quantity of data. But Andrew Wilson asked another question. This is quite an interesting one as well. With the forthcoming Night of the Long Knives to reduce the budget, is there a decision support tool to indicate the least impact from deferrals, or has this happened already? So, I could perhaps start the answer on that to say is the decision support tool is very much could help with this kind of thing, because obviously, clearly, if you're talking about deferring work, the decision support tool allows you to generate, if you like, predictions about if I don't do anything, where is this going to be in 2 years' time? So we can use them certainly in that way. We haven't actually got that far into the detail of work yet, but you could certainly use it to help do a least impact.
No, definitely. I think that's, and then the other part of it would be, you know, the work that I mentioned on the sort of system criticality and the kind of impact on timetable. You could start to look then at what the impact of, you know, if the models predicted that the SDs would make it, you know, very poor or super red or whatever, and you had to drop the speed, you could then look at like the impact on the timetable as well, if you kind of go down that route. But I think the DSTs definitely lend themselves to do that kind of analysis.
I would add, just for the benefit of it, that the government's obviously making some you know, asked us to look at making some cutbacks, which is hardly surprising considering the situation the country's in at the moment. At the moment, those cuts are aimed at our investment budget. So they're not aimed at maintenance, and they're not aimed at domestic renewals, if you like. So they're routine replacement of track. What they're aimed at the moment is some of our big investment projects. So it'll be things like electrification schemes, major remodelings, re-signallings, which are longer term things. So
I think that there's been a review of the R&D work as well over the last sort of 6 months, which I guess understandable.
Probably what it's it's going to mean putting things back rather than stopping them altogether. So
no, definitely.
Right. So I've got no more questions. Has anybody got any further questions? Or if not, I would like to call upon Lynn Duker to present a vote of thanks. Over to you, Lynn.
That's great. Thank you, Andy. And thank you also, Kevin. I'd like to propose a sincere vote of thanks to Kevin for a very comprehensive and informative presentation with some really progressive content in there. So thank you for that. So I suggest that we collectively unmute ourselves and give him a thoroughly well-deserved round of applause. Thank you, Kevin.
Okay. Right. Thank you all. Right. So first thing before I bring the meeting to a close, a really fascinating talk about what you can do with data. Before I bring the meeting to a close, are there any issues arising from the notes of the last meeting? I'll take that as a no. Okay. So let you know that upcoming meetings now, the February meeting, remember, is on the 3rd Monday in February. This was due to a clash with another online meeting. So that'll be at 5:15 on February the 15th. We've got Alex Hinchelwood coming, is doing a talk to Can We Do It Again, which is about the work that's taken place in the Conway Valley line, both to repair the damage, but also to improve the resilience for the future. And then the next meeting is 8th of March, which is Jeremy Rees coming to talk to us about Permanent Way on the Isle of Man. The 12th of April, we've got Mark Howells coming to talk to us about drainage at Cowley Bridge Junction. And that's a site which impacted, flooding there has impacted seriously on the Western in the past. And this is about the works that have been done, again, to improve our resilience and improve our recovery. And then, so at the moment, we will continue to meet online. I think nothing's going to happen certainly for the next few months. I continue to monitor the situation. The problem at the moment is still, obviously, social distancing means the meeting room that we used to use in Cardiff can now only accommodate a fraction of the people it used to have before. But I'll keep you posted on what's happening with that from now on. So,